So let's start looking at some of these example problems for the end behavior of polynomials. And we need to consider this polynomial function g of x, where it's 5x to the 6 plus a bunch of lower power terms. And recall from the last video that the main way to approach these problems is that we basically only need to look at whatever the highest power term is, and then consider what that parent function looks like. So this is x to the 6th, so we'll want to consider the parent function for y equals x to the 6th. And the reason that that's true is we're looking at very large x values. So x is going to approach infinity, or x is going to approach negative infinity, and we want to see what our function does. Does our function go up to positive infinity, or does it come down to negative infinity as x gets bigger in the positive direction? And likewise, as x gets more and more negative on our graph, does it go up to infinity or down to negative infinity? So to answer those questions, let's consider a specific x value. Let's say we're going to plug in a very large number. Let's say x is equal to a million, or 10 to the 6th power. So 1 followed by 6 zeros, which again, just more explicitly is a million, but it's going to be easier to work with as an exponent or in scientific notation. So if we plug in 10 to the 6th, we'll keep the 5 out there, and we raise it to the 6th power, and then we add 10 to the 6th, and we raise that to the 5th power, and we're not even going to consider the lower power terms because you'll be able to understand it just from looking at the closest to x to the 6th, this x to the 5th term. Now, an exponent to an exponent, we multiply. So this becomes 5 times 10 to the 36th power plus 10 to the 30th power. Now, this number here is a 5 followed by 36 zeros. And this number here is a 1 followed by 30 zeros. So, in essence, this is 1 million times bigger than this term right here. And so, it's almost like we have 5 million and then you're adding 1 to it. And adding 1 to 5 million doesn't really change the fact that the overall y value is about 5 million. So as x gets bigger and bigger, this term right here, this 5 times x to the 6th, tends to dominate the equation, and in the end is really the only term that matters. So because of that, that's why we really only need to consider the first term in these, or the highest power term. So let's first look at the parent function for x to the 6th. We went through that in the last couple videos, and we know that when x is raised to an even power, it tends to look like a parabola or a quartic, and that the higher the power, the steeper the function gets, but it still has that general parabola shape. And so x to any even power is going to look like this. Now, if we were to, let's say, make it negative, so y equals minus x to some even power, all that's going to do is just make all the y values negative. And likewise, since we'll need it later, if we look at when x to some odd power is multiplied by a negative, all that's going to do is reflect it about this x-axis just like we had here. So if the y values were negative, now they're going to be positive. And if they were positive, now they're going to be negative. So it just gives that reflection about the x-axis. And in our case, we're dealing with a positive coefficient out front. We have a 5. And the 5 really is just going to stretch it. Like for instance, if we're looking at x squared, so that's just a normal parabola, but then if we were to multiply that by, let's say, 2, all the y values are now going to be double what they used to be. So the multiplication out in front just makes it much steeper. And this is a very rough picture, but the multiplication just stretches everything. It won't actually affect the end behavior of the polynomial. So for this 5x to the 6th, we know, roughly speaking, that it will look like a parabola. it's going to look something like this as x gets really, really positive or very negative. And so we can say that as x approaches infinity, and this idea is kind of the beginning of calculus where we would take what's called a limit. In fact, in calculus, you would just write the limit as x goes to infinity of our function and determine what the function's actually approaching. But for now, we will save that notation for calculus. So we'll say x approaches infinity, and so we need to determine, and actually this is g of x, so let me be careful with my notation. What does g of x approach? And since we know that the highest power term looks like this, the parent function for y equals x to the sixth, we know that as x gets really big, that the function itself is going to shoot off to positive infinity. And likewise, let me redraw that, when x gets really negative. So now we're putting in very negative values. We ask, what does the function approach? And in this case, since it's raised to an even power and any negative number you put in here will become positive as the output since they all cancel out, the function starts to approach positive infinity when the x values get more and more negative. So in both cases for this function, it's going to shoot up to positive infinity. And again, if it was a negative out in front, it would go down in both cases. And so both of these would be negative infinity. If it's an odd power, we're going to look at that in a later example. So the answer to this is that the function in both cases goes to positive infinity, so it can't be that one and that one since those have negatives. And it can't be this one because that has a negative as well, so that leaves choice letter A for the answer to this in behavior question. So in the next video, we're going to look at 3 more examples to these just to get some more practice.